Okay, let's get started until others join. And before that, do you have any of you have any question regarding the previous lectures? Any questions, or you all good? Yeah, and the thing is, still we are laying the foundation for the spectroscopic techniques, right? So whatever already you learned some techniques and you know how to do some analysis and all these things, you're familiar with the um, some spectral analysis, but still we don't have a good idea about the hardware and the software of those systems. That's the main objective of this course, and especially this particular section, to have an have a good idea about the basic components and how we should take measurement and what are the requirements when we take the measurements, so and so. Right? And we discussed instrumental parameters and signals, noises, and all these things. And last week, let me share the screen first. Okay, can you see the screen? Is it visible?
Yes, ma'am.
Okay, thank you. So, right. Last week, we started the introduction for the spectroscopic method after talking about the all signal parts, noise part, and performance characteristics of the instruments. We started the spectroscopic method section, and I will quickly go through what we have discussed last week just to refresh. So we talked about what is known as the spectroscopy and the spectrometric methods, and also the electromagnetic radiation. And we talked that electromagnetic radiation has both wave and particle properties, and when it passes through vacuum, what it behave, and we talked about how it act as a wave and the properties, because the reason you may have already know these words, know these terminologies, but the reason I discuss these things because you may need to know these terminologies when you learn about certain spectroscopic techniques in detail. So these wordings have been given just to refresh your knowledge, okay? And we talk about the velocity and what is the speed of light and all those things, and what is happening to the light wave when it passes through medium, and the Planck's equation. And the Planck's equation is the main and fundamental equation in almost every spectroscopic technique. So we have to use this to calculate the energy differences and the wavelengths and all these things. So this is the most important equation. And we talked about the electromagnetic spectrum and how the frequency or wavelength, what are the frequencies or wavelength for particular regions of the EMR electromagnetic spectrum, and some examples of the different types of spectroscopic method, right? So this is where we stopped last week, and today also let's discuss how the waves, when it is a wave, how it how the diffraction, reflection, all these things happen, because when we talk about the diffractometry and we need to have some idea about the X-ray diffraction and the absorption, fluorescence, Raman, all these things. So before going into detail for those particular spectroscopic technique, let's study how these waves can act as in different cases, right? Okay, so the superposition of wave. So you already, you might know that the wave can act as, wave can have constructive as well as destructive interferences, right? So constructive interferences happens when the two or more different types of waves are in the same phase. So for example, here the dotted line are wave 1 and wave 2. And when these dotted waves are in the same phase, the total wave act as a, it will have constructive interference. So the amplitude or the height will be increased. And in the destructive interference means when two different waves are in different phases, let's say 180 degrees angles. So when they are when they are in different phases, there might be some destructive interferences. And these constructive and destructive interferences you will learn, for example, when you learn about the X-ray diffraction spectrophotometer. There you will have an idea about how these interferences result in the spectra, right? That is the superposition. When the superimposition of the waves happen, both constructive and destructive interferences are possible. And another property of this electromagnetic wave is diffraction. So diffraction is the bending of light as it passes through an aperture or around a small object. So you can look at this figure. This is the incoming radiation. And when there's an aperture or hole or some slit, it will go through it. But what will happen? It will diffract. The light will bend. And the amount or the extent of bending is depend on the size of this slit or the aperture, right? In the first one, in the figure A, the slit width or the aperture size is larger than the wavelength of that particular wave. So the xy is significantly higher than the lambda. Then it will bend like this. The bending is comparatively smaller than the figure B, right? But still there's a certain extent of diffraction. And in figure B, the xy or the slit width is equals to the wavelength of the radiation. So in that case, we can see the diffraction pattern. The light has been bended in a very curvy manner. So based on the slit width, the diffraction will be different. And it is a consequence of interferences. So it can be constructive and destructive interference. You will see here in this figure, parallel beam comes and it goes through the aperture A or the hole A, and it will diffract like this. So here it is an example of diffraction by a single slit. Only one slit is there, right? And when this wave passes through, and when it passes through the hole B and C, now there are two slits. What is happening? The light which passes from hole B also will diffract like this. You can see, right? And also the light which passes through the slit C, that one also will diffract like this. When these two holes diffract the incoming light, you will see here, look at the O to D direction, this one, and the O to E. And also there are some other regions that the two waves are not superimposing exactly, right? So when these two slits are there, then you will see some dark and light spots. So this is the basic in the X-ray diffraction. So you will learn when you learn about the X-ray diffractometer in detail. So that is what is happening. You will see in the X-ray diffractograms, you will see some dark and light spots. And based on these dark and light spots, we will identify the analyte. So that is what is happening in the XRD, right? That is diffraction. So any wave can undergo diffraction because any wave or any light can bend when it passes through an aperture. Then the radiation can be transmitted, right? So when the radiation or light passes through a medium, we already discussed this one, and when it passes through a medium, the velocity or the speed of that radiation will be slowed down compared to the vacuum. So when the velocity decreases or when the speed decreases, the wavelength will be decreases. And there's a thing called the refractive index. So using that refractive index, we can see how much of this velocity changes when it passes through different medium. So this equation can be used to find the refractive index. This Ni is the refractive index and C is the velocity in a vacuum, and Vi is the velocity of the radiation in the medium. So this equation, you should remember that one, how to find the refractive index. And refractive index is wavelength dependent, and also it is frequency dependent, right? That is another phenomena that waves undergo. So this one also you will use when we learn about certain spectroscopic techniques. And the dispersion. Dispersion is the variation of refractive index of a substance with a wavelength or frequency. So when the refractive index of a substance is changing with the wavelength or the frequency, dispersion can be happen. There are two types of dispersion, normal and anomalous. So what does that mean? Look at this figure, the graph. Y-axis is the refractive index and x-axis is the frequency. When the frequency changes or the wavelength changes, if you see a refractive index change like this, in this region, there's a gradual increase in the refractive index with the frequency. And in this range also, there's a gradual increase of the refractive index with the frequency. If you see something like this, the gradual increase of the refractive index with the frequency or the wavelength, that is we call as normal dispersion. And anomalous dispersion means, look at this sharp changes. In this range, the refractive index changes very sharply. So that frequency range, when there's a sharp change in the refractive index, that frequency range we call as in that range anomalous dispersion happens, right? And the refraction of radiation is another.
Excuse me, madam.
Yeah.
I have a question, madam. Could you please go to the previous slide?
Okay. Yes.
Madam, in the anomalous dispersion, in here, in the both cases, we see a gradual decrease. So,
Yes.
is it only gradual decrease, not a gradual decrease, but a sharp decrease? Is
Yeah.
it only in sharp decreases we say anomalous dispersion, or madam, if there is a like anomalous like increase, can we also
yeah, normally we call the sharp decrease, right? Only for the sharp changes means the only for decreasing part, we call the anomalous dispersion. That's the normal way, right? But
okay,
for example, let's say your question is if there's a sharp increase of the refractive index, can we say as an anomalous dispersion? That's your question, right?
Yes, madam.
Yeah, normal case is the decrease, but there might be certain cases sharp increments of the refractive index happen. If it is a sharp, if the change is sharp with a really small frequency range, we can call it as the anomalous, right? Anomalous dispersion, if it is not gradual change. Is that clear?
Oh, okay, so in both cases, we can use it. Right?
Yes, if it is not gradual change, or if it is a sharp change in the refractive index, we can say it's anomalous. But normally, most of the cases, you will see these type of decreasing patterns, right?
Okay, madam, thank you.
But if there's a certain case, if you see sharp increase or sharp change, then in that case also we can say, okay, that is also anomalous dispersion. The definition is there should be a sharp change in the refractive index in a very low frequency range, right?
Okay, madam, thank you.
Okay, so is that clear to all? Okay, so this one also, the normal dispersion also, it can be refractive index can be increase or it can be decrease, but in normal dispersion also it should be a gradual increase or decrease thing, right? Yes. Then the refraction of radiation. So refraction, this one actually you might learn this when you were in the O-level classes also, refraction. So you see when the light passes through from one region to another, the light can be bent. For example, if we put some rod or anything to a glass of water, you will see the bending of this rod or pencil or whatever things. So this is because of the refraction of the radiation. So the refraction, in the refraction, we will apply, there's a law called Snell's law. Snell's law. So that is the law that we can find the, here also we can find the angle of refraction, and the, if we know the angle, we can find the refractive index like this. So when light passes through the medium 1 to medium 2, the light wave can bend, right? And the angles theta 1, theta 2 are different, and according to the Snell's law, sine theta 1 over sine theta 2 equals n2 over n1. N is the refractive index of the medium, right? And it is equals to the velocities, because using this equation, the refractive index and velocity of the medium has inverse proportionality, right? Inverse relationship. And that's why n2 over n1 equals v1 over v2. So this equation also you will be used when you do the calculations and when you learn other techniques. And for transmission from vacuum or air to another medium, this equation can be simplified as this. The reason is the refractive index of vacuum is n. N for the vacuum is 1, and for the air it's 1.0000 something. So therefore we can assume that both vacuum and air, the refractive index equals to 1. Therefore, then N1 becomes 1, then we can simplify this equation to N2 equals sine theta 1 over sine theta 2. So when we know the theta values, if we can find the theta values, then we can find the refractive index of certain media. And also if we know the refractive index and if we know the theta 1 value, then we can find theta 2 likewise. So we can simplify that equation. And the reflection. The reflection is another phenomena that any radiation can undergo. So what is happening when there's an interface, or when there are two different media, the light can reflect and light can go in a different direction, but the light returns to the medium which it originates, or it returns back to the initial medium. So we call it as the reflection. And there are two different types of reflections: specular reflection and diffuse reflection. And look at this picture. If there's a mirror-like thing, or if there's a smooth surface like this, then we can see mirror image from the because of the reflection. And reflections on still water are an example of specular reflection. So that is when there's a smooth surface. And in the diffuse reflection, the surface is not smooth and surface is rough, and the light reflect in all directions. So the light will be diffuse. This diffuse reflection, there's a spectroscopic technique called diffuse reflection spectrophotometer. So in that case, this phenomena will be used, diffuse reflection of radiation. Right? So that is how the reflection can happen. And when there's a rough surface, when it happens the diffuse reflection, we will not get a nice image like the specular reflection. So we will have some blurred image. We will not get a nice image from a rough surface. And the scattering. Scattering is actually, it's almost everywhere. So even in the UV, also UV, when we talk about the UV, you know, the incident light comes and the incident radiation can be absorbed, scattered, or transmit by the sample analyte in the sample, right? Analytes in the sample. But in that case, we are measuring the transmitted light in the UV. We don't measure the scattered light. We measure only the transmitted light. By measuring the transmitted light, we can tell how much of light has been absorbed. But if we think, you know, in the UV, we pass the incident light and we measure the transmitted light and we tell how much of light has been absorbed. But we don't talk about how much of light has been scattered there. When we calculate the light absorbed in the UV, there are certain amounts scattered also include, but we are not paying attention to that one, right? And the scattering is, this figure shows you how the scatter happen. When the light comes, then it will the transmitted at all angles from its original path. So when the light hits the small particles, these particles, it can transmit from all direction. There's no any particular direction. So it can pass or it can transmit in all direction. And also scattering is possible. Suppose there's a one over here, one particle here, light pass through this particle and scatter certain and then transmit certain. Then that transmitted light can also go and hit the next particle. In that case, certain amount of light can be again scattered from that particle. And then rest will transmit. So like that, when the particle size are getting larger and larger, you will see more and more scattering. And there are different types of scattering. The Rayleigh scattering is one. Rayleigh scattering means when there are molecules or aggregates of molecules with dimensions which are significantly smaller than that of the lambda of the radiation. So when the molecule size is smaller than the wavelength of that particular incident radiation, this type of scattering can happen, Rayleigh scattering. And the Rayleigh scattering, you will learn about the Rayleigh scattering in more detail when you learn Raman spectroscopy. So the Rayleigh scattering is more important in Raman spectroscopy. In that case, the intensity of the radiation proportional to the inverse fourth power of the wavelength, lambda minus 4. Inverse fourth power of the inverse fourth power of the lambda of that particular radiation. So in order to happen the Rayleigh scattering, the particle size should be significantly small than the wavelength. And there's another one that is for the Rayleigh is for the really small particles. And when there are big molecules, scattering can happen when there are big molecules also. And we call it as Tyndall effect. In that case, the colloidal dimensions of particle is really large. The dimensions are large and the scattering can be seen. For example, if you get a titanium dioxide sample, you will see a cloudy sample, like milkish color sample. The reason is that in that sample, the size of the particles are really big. Therefore, we can see some cloudiness. That cloudiness is, one of the reasons for that cloudiness is the scattering of the particle, right? So this Tyndall effect can be used to measure particle size, shapes of polymer molecules, because polymer molecules are really big molecules. And the Raman scattering. The Raman scattering, again, that one also can be seen. It will be talked when we talk about the Raman spectroscopy, Raman and Rayleigh scattering, and there are called the resonance Rayleigh, resonance Raman, all these things, and you will learn that one in detail later. And in the Raman scattering involves quantized frequency changes. So here, when it is Raman scattering, the transitions, it is a result of vibrational energy level transitions that occurs in the molecule as a consequence of polarization process. So you know the Raman associate with the polarization of the molecule. So here the scattering happens because of the vibrational energy level changes. And there are some peaks called Stokes peaks, anti-Stokes peaks, and Rayleigh peaks in the Raman. So those are because of the this type of scattering. So the Raman spectroscopy is one of the main thing that scattering process is used. But in other one also scattering is there. As I told you, in the UV scattering is there, but we are not measuring the UV scattering. However, there are certain research undergoing. There are certain mathematical formula, and people have done several researches to find the scattering component of the UV spectra as well. So normally we call the UV absorption, but when we take the UV spectrum, it is not only the absorption, it has both absorption as well as scattering. Therefore, the correct terminology is UV extinction, right? So sometimes when you read articles, when you do research, when you read articles, you will come across with that terminology, UV extinction. UV extinction is the most accurate term. In that case, extinction has both absorption part as well as scattering part, right? So that is about the scattering of radiation and the polarization. The polarization means normally when we take a radiation, it has, you can see, it has the vibrations in all directions, right? You will see the blue color things are the vibrations. So those vibrations are equally distributed in different planes. So if you see here, this is the normal light, and we can represent that the light with vibration in the figure B. So that is the unpolarized. Normally that is how the radiation, how it looks like. But there are sometimes we can use a polarizer. There are some what is not instruments, some we can say some gadgets which are called as polarizer. If we use a polarizer, then we can have polarization. So that means if there's suppose there's a vertical polarizer. So if we use a vertical polarizer, it will pass only the wavelengths in the vertical direction. Just imagine like a hole. We have a cardboard thing and we are making a vertical hole, and if we put it in front of this wave, if the hole is vertical rectangular one, and if we put it in front of this, then only the light in the vertical direction will pass through that aperture, right? Aperture or that hole. But the rest will not pass through. So that type of things we call as polarization. So here in figure C, this one is the plane polarized on the vertical axis. And similarly, if we need, we can do the polarization in horizontal axis as well. So we just have a polarizer and we will polarize the light in horizontal direction. These polarization things can be used. There are certain situations in the fluorescence also. This polarization is possible in the some fluorescence spectrophotometer. These polarizers are available, and we can call it as fluorescence anisotropy. So I will not going to talk in detail about these things. So in that, when we take that anisotropy measurements, there are some polarizers in horizontal direction, vertical direction. So in that case also, we can polarize the radiation. Okay, so those are some examples of the waves, that wave nature of the electromagnetic particles, right? So diffraction, reflection, all the polarization, scattering, all these things can happen as a wave. And next, let's talk about how the radiation interact with the matter. So that is another most important thing in this when we talk about the spectroscopy, because when we talk about the spectroscopy, main thing happens is the it's when the light or whatever the radiation passes through the sample, it will interact with the analytes present in the sample. Then because of that interaction, we will see a signal. Therefore, it is really important to study what are the types of interaction of the radiation with matter. Okay, the first one is the emission and chemiluminescence process. So here, the sample is excited by the application of thermal, electrical or chemical energy. So the sample or the matter is here and the sample will be excited. The excitation source, as the excitation source, thermal energy, electrical or chemical energy will be used. And what is happening when this energy interact with the matter, there might be emission. So if it is if the input energy is thermal or electrical energy, we call it as a emission. But if it is a chemical energy, that emission light we call as chemiluminescence, because the input is because of a chemical energy. That means energy which comes as a result of a chemical reaction. So that type of situation we call it as chemiluminescence. Right, so this is the figure B is the energy level diagram of the emission or chemiluminescence process. So what is happening? This zero ground state, and these are the excited state. When it absorbs energy, it will goes to the ground excited state. Right? So excitation happens, then after certain time, the relaxation happens and the emission of a photon, the absorbed photon will be emit. And I think you know, in order to happen these transitions, the input energy should be exactly equals to the energy difference. of this energy states, right? For example, the delta E values should be matched with the incoming photon energy. And when the relaxation happens, you can see the figure C, the lambda 1, the intensity is highest here. The lambda 1 is the transition from first excited state to the ground state, this one. Because the intensity, the reason the intensity is highest here, now all the excited electrons in this first energy state, first excited states, will come back to the ground state, and also certain amount of the energy which goes from second excited state to the first one also, then it will also come with this transition. That's why the intensity of this transition is highest. And the lambda 2 is the electron transition from the second excited state to the ground level. And that one also, since the energy difference is higher, the lambda is lower. E equals hc over lambda. That's the equation. And the transition from second excited state to first excited state is really small. And again, the energy difference is small, therefore lambda value is high. So this is the representation of the spectrum of these transitions. So this one is an example of the emission or the chemiluminescence process. And absorption also can happen. So emission or chemiluminescence will be used in atomic emission spectroscopy and some other emission spectroscopic technique. And the absorption is used in UV absorption and other types of absorption things. So this is what is happening in the absorption process. So incident radiation goes to the sample and transmitted certain radiation. So we will measure the transmitted one. In the real situation, we will be able to detect the transmitted one, and by taking the difference, we will measure the absorption. Right. So this is the energy level diagram. When the photon with the correct energy comes, the electrons in the ground state will go to the excited state, and like this. So the E1 and E2, the energy difference of E1 is smaller compared to E2, therefore the lambda 1 is larger compared to the lambda 2. Right? That is absorption. And the photoluminescence, like fluorescence and phosphorescence. This is another type of interaction can happen. Fluorescence and phosphorescence. So what is happening when the incident radiation comes, it will have some non-radiative decays and also some intersystem crossing. Have you heard about the Jablonski diagram? Have you learned that one?
Yes, sir.
You learned?
Yes, sir.
Okay. Have you learned the fluorescence spectrophotometer? Fluorescence one? Have you learned anywhere or not yet?
We have learned the theory part of it, madam.
Okay. I think under photochemistry, you have a section Am I correct? Fluorescence? I don't know whether.
Yes, madam.
Yeah,
Yes.
yeah. So you can remember when you draw the Jablonski diagram, and if you remember, you draw arrows, the excitation, and then some singlet states, triplet states, and here the inter-system crossing, internal conversion, all these things you draw. And when we comes to the fluorescence, it goes to singlet state, but in the phosphorescence, the electrons will jump to the triplet state. So for that electron transition, it will take some time. Therefore, there will be a certain delay in the phosphorescence compared to the fluorescence. That is that time delay cause that is the main difference of the phosphorescence and fluorescence method, right? So here in the energy level diagram, look at this one. So absorption happens and the electrons move to the higher levels. Then excess energy will be released and some non-radiative decay can happen, and electron will jump back to the ground state. So the energy or the light, not the energy, the light which emits during that relaxation process is called as the fluorescence. And in the phosphorescence, when here, instead of coming back from the singlet to the ground state, it will goes to the another triplet state, and the electron will be there certain time, and then it come back to the ground state. So this delay, because of that time lag, we call that one as the phosphorescence. And the emission occurs over all angles, and the wavelength emitted correspond to the energy differences between levels. See, the major distinction between fluorescence and phosphorescence is the time scale of emission, with fluorescence being prompt and phosphorescence being delayed. This delay is because of that transition. And so that is how the fluorescence and phosphorescence or photoluminescence methods happens. And inelastic scattering in Raman spectroscopy. When scattering happens, it can be either elastic scattering or inelastic scattering. The elastic scattering means there's no any energy change. Elastic, you know, elastic, it's some pratyast or something. So there's no any energy change. It's elastic. When it comes to the inelastic, there are certain change of energy associated with that scattering process. Maybe energy will be increase or decrease. Those type of scattering is a one main feature in the Raman spectroscopy. So have you learned Raman spectroscopy along with the vibrational spectroscopic techniques? You familiar with the Raman, or you have not studied Raman?
We had a lesson in last semester, madam.
You had a lesson you mean last semester or last year?
Last
semester. Okay. So have you learned about the Stokes shift, anti-Stokes shift and all these things? Or no?
Yes, madam, we have that.
Okay. So then you know about this one also. I just want to make sure whether you are familiar with the terminologies. So in the Raman, this inelastic scattering happens, right? So there might be certain energy gain or loss during the scattering process. So when we talk about the Raman, Rayleigh scattering and Rayleigh shift And Stokes shift and anti-Stokes shifts are three main types of shifts that we are talking. So here this spectrum, Stokes and anti-Stokes shifts. Sometimes we call this peak as a resonance relay. Resonance relay means the excited one and the emitted radiation, the energy is same. When the energy or wavelength is same, we can tell it as the resonance. So that these types of changes or the scattering changes can happen in the Raman spectroscopy. It's all because of this inelastic scattering. And if you remember, when you learned the Raman spectroscopy, you might have heard about the virtual states. So this is the virtual state. The electron jump to a virtual level, right? So that's why we represent this energy level as the represent this energy level using a dotted line instead of solid line. So while this Raman is, or this one also associated with vibrational energy level, and when it absorbs energy, it will jump to a virtual state. So the transition level will be somewhere here. The energy is not enough to transfer the electrons to the next transition level, right? But it will go to a virtual state, and then it comes back to either first vibrational level, or when it comes to the first vibrational level, now there's some vibrational level energy difference, excitation and UV. So this type of energy difference is there. So when it happens, this type of transitions we call as a Stokes shift. And when the electrons in the first vibrational energy goes to the virtual state, and when it comes back to the zeroth level, then there's another difference here. This type of transition we call as anti-Stokes, Stokes and anti-Stokes, and the Rayleigh scattering here. And in the Raman, there are some resonance Raman spectroscopy, Rayleigh spectroscopy, and surface enhanced Raman. So lots of things. Surface enhanced Raman means it detects the surface of the molecule, not the molecule. Most cases, molecular aggregates, right? So all these things, I'm sure you will not learn much in detail, but you will be able to learn all these things. So when you learn all these things, remember it has this type of scattering processes. When the radiation interact with the matter in the inelastic nature, these signals are arising, right? That is in the Raman. Okay, so far we learned about the interaction of radiation with matter. What are the different types of interaction of radiation? So you will apply those types of interactions when you learn the different techniques, right? So maybe you will feel like we are just touching everything, but after you finish all these things, you should be able to correlate these things with the special or particular spectroscopic techniques, right? Right. And another thing we should learn, this is also a basic thing. We will need these things when we talk about the next section. Line spectra, band spectra, and continuum spectra, right? Line spectra. Line spectra happens from the individual atoms. So in the individual atom, when it absorbs energy and when it excited, then the emission happens. when there's no any molecules, when it is just an atom, so we will see some discrete lines. For example, it has only transition level like 3s, 3p. This is from, let's say, from sodium. So the electrons, the outer electrons in the sodium atom, not the molecule, anything. This is line spectra for atoms. So atom will absorb energy and it will goes to the excited state, and when it comes back to the ground state, it will emit certain radiations with certain wavelength. So, for example, in the atomic emission spectroscopy, we will be able to see well separated discrete lines, right? But when it comes to the small molecules or radicals, we will not be able to see lines. Instead of lines, we will see bands. Most of the time it is Gaussian shaped bands, so we will see bands. This is because in the molecule, unlike the atoms, vibrational energy levels are there. Therefore, even though when it excited to the higher excitation state, when it comes back to the ground level, it can comes back to different vibrational levels. So because of that, there might be range of wavelength. So if it is a molecule, always the bands will be there. Most frequent thing is the Gaussian shaped bands. And the continuum spectra. So you will see, you will see these type of things when you learn some sources. So when there are some blackbody radiation, when you learn the blackbody radiation, you will see the energy change with the wavelength like this type of change. So this continuum spectra will be from the blackbody radiation, and when it happens when the solids are heated. So I included this one because when we talk about the sources, we will talk about it in next section, the sources of the optical instruments. So you will come across with this xenon arc lamp, tungsten lamp, all these things. That's why I put this continuum spectra here. Right, so the line spectrum, band spectrum, and the continuum spectra are three different types of spectra you will observe. Okay, now those things that we have learned so far for 2.5 days are the really basic things. So it is for the all instruments. And next, let's discuss about the optical instruments. The first, what we are going to talk next is the components of optical instrument. Here also, I will not going to talk in detail in different optical techniques, but basic components of optical instrument will be discussed here, right? And do you have any questions so far from the previous discussed thing? And if you have, if you need to know much details, I again telling you, please go and refer the textbook. It has lots of details, but don't worry if you don't understand certain things. In the undergraduate level, we are not expecting you to understand all these things, because this textbook is also used by the graduate students when they learn the analytical chemistry or the instrumental analysis. So no need to worry. Even though there are lots of details, and if it is difficult to understand, that's fine, but it's worthy to read it, right? Okay, then if you don't have any question, let's move to this section, components of the optical instrument. Okay, so this says UV, visible, IR have enough features in common that they are often called optical instrument, and but human eye is not sensitive to UV or IR region. Human eye is sensitive to visible region, but human eye is not sensitive to UV or IR region. So we should have some way to detect the things in the UV and IR region. So under this optical spectroscopy, most cases the UV, vis and IR will be discussed. Okay, these optical spectroscopic methods are based on 6 phenomena. These 6 are the main phenomena associated with the optical spectroscopic technique: absorption, fluorescence, phosphorescence, scattering, emission, and the chemiluminescence. So we will, when we learn the basic components, we will discuss how those components are present in these different cases. Right. Now let's see what are the main components of a typical spectrophotometric spectroscopy instrument. So typical spectroscopic instrument means whatever the spectroscopy instrument, these components should be there. I think if you remember, we talk about the talk in the very first lecture also, there should be a source of radiation. So the radiation source should be there. It is a must, right? And next is the wavelength selector. So wavelength selector means a device that isolates a restricted region of the spectrum for the measurement. So if we talk about the spectrum, and let's say if we talk about the source might have the different regions of the wavelength. It will emit relatively large wavelength range, but we may not interest in that entire range. In that case, there should be a way to select the desired wavelength range. To select that desired wavelength range, there should be a wavelength selector, right? So most of the time, monochromators, gratings, and filters will be used in the wavelength selector. We will discuss this one separately, but that one is another most important component: source and the wavelength selector. And sample cell. So sample cells, it's again important because there should be a place to hold the sample or hold the analyte. So the sample cell should be a transparent container, right? That is another main important component. And the detector. So without detector, there's no way for us to detect the signal. So a radiation detector, it converts radiant energy to a usable electrical signal. So remember, in the first day we talk about the transducer changes the electrical signal to non-electrical signal to electrical signals, and then again electrical signal will be converted into some other non-electrical things, and in the detector, there's a conversion and there's a transducer thing. All these things we learned in the very first day. And this detector, and in that day also I told you I will discuss those things in detail. So here where we are going to talk about these detectors, sources, and all these things in detail. We will talk about those things in detail in this section. So therefore, if we don't have a detector, there's no way that we can get an idea about the analyte. There's no way we can get the information from the sample. And the signal processor and readout. So that readout device will be placed after the detector. When the detector detects the signal, when it detects any changes in the signal, then there should be a way for us to identify. So the signal processor or readout device will display the transduced signal. So most of the cases, this readout device is a computer. So nowadays the computers are the main readout devices. So there should be a readout device. Okay. So these are the 5 major components available in any spectroscopic instrument. So if someone asks you to draw a block diagram or what are the components of the spectroscopic instrument, remember you should have these 5 types of the 5 different types along with some other gadgets, right? So these are the main or essential parts of any spectroscopic instrument. Right. Now let's go and see in the absorption spectrophotometer how these 5 different components are arranged. So remember this: source, wavelength selector, sample cell, detector, and a readout device. So here the first one, source. In the absorption spectroscopy, the source, first one is there should be a some light source, and after the light source, wavelength selector should be placed in the absorption spectroscopy. Then when it selects a particular wavelength from the source, that particular wavelength will go through the sample. So wavelength selector, monochromator is one type of wavelength selector. We will discuss that one in detail. So, and once the monochromator or filter or whatever the things select the wavelength, that particular wavelength will go through the sample, and then detector will detect it, and signal processor and readout device will show us a signal. That is how these 5 different components arrange in absorption spectroscopy. And when it comes to the fluorescence, the arrangement is a little bit different. And if you remember, the fluorescence cell, in the fluorimeter, we talk about the 90 degrees angle, right? We are talking about the 90 degrees angle of the source and the detector. And here the source, this is the excitation source, excitation light source, and then the wavelength selector will select the wavelength range of the excitation, and then the excitation wavelength will goes to the sample, then the emission will happen. the emitted radiation will pass through the wavelength selector here. This is for the emission wavelength selector. Then that emitted radiation will be detected by the detector, and finally we will be able to see the fluorescence signal. And in the absorption spectroscopy, the sample, normally the sample cell is a cuvette, or we call it as a sample cell or cuvette. In that case, if you are, I'm pretty sure you have seen the quartz cell or the glass cell, both are fine. Quartz is for the UV. We cannot measure UV from a glass cell. In order to measure UV range, we should have the quartz cell, and the using glass cell, we can measure only the visible range. So if you remember, you can, in that UV cell, two sides are clear sides and two sides are rough surfaces. So it is okay even if we have only two sides, because the wavelength passes from here to here in the one direction. The radiation goes through only single direction. Therefore, it is okay, we can have two rough surfaces and two clear surfaces. But in the fluorescence, since the light or radiation passes in 90 degrees angle, the sample cell should be clear in all four directions. Otherwise, if we have two rough surfaces like this, then the light cannot pass through and we will not be able to see the signal. So therefore, in the fluorescence cells should have clear surfaces in all four surfaces. Right. Now that is absorption and fluorescence. Next, emission. So emission, example is the atomic emission spectroscopy. So in the emission, you can remember we use a nebulizer and we insert that nebulizer into the sample and then nebulize and make the sample convert it into atoms, and then that one we pass through the wavelength selector. So here the source sample is here, source is here, and you can see a flame. So it will be a flame or plasma. In the atomic emission, we can use the flame atomization, and also the ICP-MS, inductively coupled plasma mass spectroscopy. Also there's a plasma, and using that source, it can atomize the sample, and then it will go through the wavelength selector, then detector, and we can see the signal. So in three different situations, absorption, fluorescence, and emission, look at how these five different components arrange. It is not same. So you should be able to draw this block diagram. If someone asks what is the block diagram for, let's say, UV visible spectrophotometer, you should be able to draw it and remember how these things are arranged, and the fluorescence, how those five different components are arranged, and all these things you have to have an idea about the arrangement. Okay, so this is the block diagram, and then let's talk in detail about each and every component. What are the sources and what are the requirements of sources, wavelength selector, all these things, let's discuss in detail. All right, and before we go to sources, this This one shows construction materials and wavelength selectors for spectroscopic instrument. Okay, so here the first part is for materials for cells, windows, lenses, and prisms. Okay, so for different region, for UV, visible, near IR, near IR, far IR, for different regions, we can use different materials to make cells, windows, lenses, and all these things. So look at here, lithium fluoride can be applied in this range. Fused silica or quartz, corex glass. See, I mentioned you UV. For the UV, we should have the quartz cells, and for the visible, we can use glass. This is the reason. See, the silicate glass or corex glass, the range lies in between little amount of UV and almost 400 to, let's say, 2000 range. Therefore, if we use sample cell with the glass, silicate or corex glass, we will not be able to get a signal in the UV range. So that's why we call that we should have quartz cells to get UV measurements. And for the IR also, if you remember, for the IR we use KBR pellets and all those things. See, it ranges in this range. So go through this graph and see what are the possible materials for different spectral region. And the bottom part is for the wavelength selector, continuum and discontinuous. We will discuss this in detail when we go to the wavelength selector range section. So yeah, it has all the prism and gratings, filters, and all these things. We will discuss this one later when we talk about the wavelength selectors. And next, let's move to sources. So now we are going to study those 5 different types. First one is the sources. So what are the sources? And the source must generate a beam of radiation with sufficient power for easy detection and measurement. So it is clear. So it should generate radiation with sufficient power. And it should be the source, the generated radiation from the source should be sufficient for easy detection. And also the output should be stable for a reasonable period of time, because the output of the source is not, if it is not stable, then it is difficult for us to do the detection. And there are 2 types of sources, continuum and line source. Okay, so you remember I showed you that blackbody radiation thing. So this type of radiation happens in the continuum source, and the line source, only a single wavelengths will be there when we use line source. So these are the examples of sources and detectors. I'm sorry, detectors also there, but we should not talk about the detectors here. Let's talk about the source, or let's talk only about the sources. And when it comes to sources, you have heard about the xenon lamp, argon lamp, and deuterium lamp, and all these things are familiar to you. And the UVs, deuterium lamps, xenon lamps are being used, and hollow cathode lamps, and lasers. Lasers are, actually we should pay much attention for lasers, because it is the most used source in the Raman spectroscopy. So the laser optics are using in that Raman spectroscopy, and also these lasers have different important characteristic, but I will not talk much details about the lasers here. Let's see if the time is available, I will come back to the laser part, and separately I will discuss this lasers, but it's only if the time is available. And here these different types of sources, let's discuss in detail. So continuum sources. So the continuum sources emit radiation that changes in intensity only slowly as a function of wavelength, right? And widely used in absorption and fluorescence spectroscopy. These are examples. For UV range, as the source we can use deuterium lamp. That is the most common source that has been used. And also the high pressure gas filled arc lamps like xenon arc, argon arc, and mercury also can be used in the UV range. And the visible range, tungsten filament lamp, that is one of the widely used thing for the visible. And for the IR, inert solid heated to this temperature. So see, for the IR, nichrome wire, global silicon carbide, all these things can be used as the continuum source. And the line sources, as we discussed earlier, these line sources emit few discrete lines. Line sources are widely used in atomic absorption, atomic fluorescence, and molecular fluorescence, and Raman spectroscopy. So line sources are widely used in this spectroscopic technique. And mercury and sodium vapor lamps provide relatively few sharp lines in the UV and visible range. Hollow cathode lamps and electrodeless discharge lamps are used in atomic absorption and fluorescence. So these are some examples of examples where the line sources are using. And even though I have not written in the Raman spectroscopy, the lasers are the line source that is widely used in Raman spectroscopy. And the wavelength selector, now that is the source, and the second one is the wavelength selector. Right? Any question from the source? I hope it's clear. And if you have any question, please you can interrupt me while I'm talking. And if you need, you can write your question in the chat box also, or else just raise your hand. You can click the raise hand here and ask the question, right? Okay. The second one, let's move to the second one, wavelength selectors. So as the name implies, the wavelength selector select the wavelength of light. So it select the desired wavelength. And normally from the what we are expecting from the wavelength selector is the radiation of single wavelength or frequency. That is the output. That's what we are expecting. Single wavelength or single frequency. But in actually, it is difficult for us to get a single wavelength, right? Instead of single wavelength, we will get this type of spectral band. So that is the wavelength that we are interested in. And it is difficult for us to get a single value, but we will get a wavelength like this, the wave band. So here the effective bandwidth. Effective bandwidth means the bandwidth of this peak at half peak height, right? So the peak height is half the width of the band, called as the effective bandwidth. When the effective bandwidth is smaller and smaller, when it getting smaller and smaller, then the wavelength range that we are measuring is getting smaller. So then we can say, okay, that is a really good wavelength selector. So we can select particular wavelength. So effective bandwidth should be relatively small for a good wavelength selector. And there are two types of wavelength selectors. We can either use filters or we can use monochromators. I'm pretty sure you have heard about both these terminologies before, filters and monochromator. And also you used filters when you use the colorimeters. So you use different filters, right? And in the UV visible spectrophotometer also, there are some monochromators. I don't know whether you have seen the monochromators. I'm not sure that one, but there are monochromators in the UVVs and the colorimeters. You may have seen the filters that we are using. Those are wavelength selectors. And filters can be two types. It can be interference filters or absorption filters. So there are two types of filters. The interference filters. Remember, we today at the very first slide, we talk about the destructive, I think it's the very first one, destructive interference and constructive interferences. So those type of interferences and the dispersion things, diffraction can happen in these interference filters, right? And in the absorption filters, as the name implies, it will absorb certain wavelengths and it will pass certain wavelengths. Now let's discuss about these two types, interference and absorption filters. Okay, in the interference filters, this is the structure. It has it has a dielectric layer, you can see it, and by surrounding the dielectric layer, there's a metal film and then glass plate like this, right? So the dielectric layer is is surrounded by two metallic films. What is happening now? The light comes, incident or white radiation comes from this direction. Then when it enters to the filter, what is happening now? The medium is changing, right? And you can see in the figure B, this is when the light enters, the medium is changing. Then some of the radiation will reflect, right? And some of the radiation will transmit. What is happening? Suppose this AB range is the dielectric layer, and when the light enters the dielectric layer, some will reflect and some will transfer. And again it comes to the other interface, bottom interface. Again, some will reflect and some will transmit. So every entire wavelength that is come as from the source will not go through the filter. Certain amount will reflect and certain amount will transmit. So that from this reflection and transmission, we can get rid of certain wavelengths of the light, and we can pass the certain wavelengths through the filter. So that is some way, or for a certain extent, we can select the wavelengths which is go to the sample. Right, from this direction, the white radiation or all wavelengths will come, and then some will reflect. Only certain wavelengths will be transmitted. So this transmitted wavelength will go to the sample, and in that case, by using this interference filter, we can have some selected wavelengths. So that is what happens in the interference filter, and this description tells what is happening. So there's a dielectric layer and the radiation hits filter, some reflected, some transmitted. If proper radiation lambda reflected light in phase with incoming radiation. Okay, so there are some destructive interferences and constructive interferences. So you remember, constructive interferences happens when the phase of two different waves are in the same phase. Constructive interferences happen when it is in different phases. The destructive interferences will be there, and if the constructive interference happens, it will transmit through the filter, and if the destructive interference happens, it will blocked by the filter. So because of these interferences, now the range of lambda is, narrow range of lambda is transmitted. So not the entire things which is coming, but a certain wavelength will be passed through the field. Okay, so that is what happens in the interference filter. Right, and the absorption filter. So you remember the colored glass you use was an absorption filter. So in the interference filter, normally the bandwidth is around 10 nanometer. I told you the bandwidth, when the bandwidth getting smaller, it is a good wavelength selector, right? But with the absorption filter, it will have broader bandwidth, like 50 to 100 nanometers. So compared to the absorption filter, interference filters are better because it has shorter shorter bandwidths. And glass absorbs certain lambdas while transmitting others. So that is what happening. It absorbs, the colored glass will absorb certain wavelengths while it will transmit in certain wavelengths. The types of absorption filters are band pass filters and cutoff filters. So band pass filters, that one passes 50 to 100 nanometers, and cutoff filters, it will cut certain wavelengths. Right, after it will only pass certain wavelength and it will cut certain wavelengths. Normally in the example is high pass cutoff filter. In that case, it passes high wavelengths, blocks low wavelength. So in the high pass cutoff filter, the higher wavelengths will be transmitted, but it will block the lower wavelength. So example of the example of this type of things used can be in emission of fluorescence. Those are some example of the cutoff filter where we can use the cutoff filters, right? So those are two different types of filter, interference filters and cutoff filters. So wavelength selector, there are two types, filters and monochromators. In the filters, interference filters and cutoff filters, we discuss these two. Now let's see what are the monochromators and monochromators. So monochromators are designed for spectral scanning. And if you remember, when you use the colorimeter, you use a filter and you measure the signal at particular wavelength, right? Signal intensity at particular wavelength. But when you use UVV spectrophotometer, you will be able to get a nice spectrum. X-axis is wavelength, y-axis is the intensity or absorption. So you will get a nice spectrum for the absorption versus wavelength. In that case, we don't just have a single wavelength, but we have a range of wavelength, right? So when we have the range of wavelength, then there should be a wavelength selector with the range of wavelength. So in that case, normally in the UVV spectrophotometer, the wavelength selectors that we use are monochromators, right? The monochromators, when we talk about the monochromators, there are two types of monochromators. So the grating monochromator and prism. Czerny-Turner grating monochromator. We call the Czerny-Turner grating monochromator here. That grating monochromator, this figure A is the Czerny-Turner grating monochromator, and the figure B is the Bunsen prism monochromator. Sometimes we don't say the Bunsen prism, instead we call as a prism monochromator, and instead of Czerny-Turner grating monochromator, we call as a grating monochromator. Grating monochromator, prism monochromator it's also fine, right? And A is for the grating monochromator, B is for the prism monochromator. And let's see what is happening here. In the grating monochromator, now the light source, the radiation will come from the light source and it will enter from this slit, right? Light will enter from the entrance slit. There's an entrance slit. And when light enters from the entrance slit, then it will pass and it will go, there's a concave mirror, and this light will focus on the mirror, the concave mirror. Then what is happening from this mirror, the incoming radiation will convert into parallel beam. Now you see the beam is parallel. See, light comes, and now after reflecting from this mirror, now the beam is reflecting as a parallel beam. Then this parallel beam will come to the reflection gradient. This is the reflection gradient. And the surface is not a smooth one. It has some rough surface. I will show you a much zoomed in picture of this reflection grating later. And now the parallel beams comes and it will hit the reflection grating, and again it will reflect to another concave mirror. Now the parallel beams, it's not parallel, it's again focused and then it goes back to the concave mirror. We call them as collimating mirrors also. And then again from this concave mirror, it will focus. You see, the light will focus. We call this as focal plane. This plane as focal plane, right? And the light will focus like this. Different reflected radiation here, and it will focus. And different lambda values will focus on different places on the focal plane. In the focal plane, lambda 1 will be here, lambda 2, 3, 4. Likewise, different wavelengths will be focused at different places from A to B. And now there's an exit slit. If we place the exit slit here, only the lambda 2 wavelengths will be exit from the slit, right? Only this particular wavelength will exit from the slit and it will go to the sample. So different wavelengths entered the grating and it undergoes some reflections, and after the reflection it will exit only a particular wavelength, and that particular wavelength will goes to the sample. So that is what happens in the monochromator. Let's go back. Okay, in this slide, in the next slide, I showed you the components of the grating monochromator. Let's go back to the previous one after referring this slide, okay? And the components of the grating monochromator is entrance slit, collimating mirror, or this is the concave mirrors we call as collimating optics, and gratings, focusing optics. So the collimating optics and collimating optics and focusing optics those are the concave mirrors, right? And exit slit at focal plane of focusing optic. So those are the 5 different types. Again, let's go back to the monochromator again. So it has entrance slit, and this concave mirror, we call it as a collimating mirror or collimating optic. It makes the beam into parallel beam. Then the grating, it reflects the radiation. And then there's another concave mirror. We call it as focusing optic, right? Because this one will focus the light on the focal plane. That's why we call it as focusing optic. So it will go back to it will focus light on focal plane, and then exit slit will exit the selected wavelength, radiation with selected wavelength. So that is what happens in the monochromators. And in the prism monochromators, this is the grating monochromators, it has a grating. And the prism monochromators, same thing. I hope you remember when we put a prism and when we pass the incident light through the prism, we will be able to see rainbow colors. So when you were kids, I think you did that experiment when you were small. So you will be able to see a rainbow when we place the prism. And same thing happens here in the prism monochromator. Same as the grating one, there's an entrance slit. Now light goes through the entrance slit, and the collimating mirror, it makes the light path into parallel line. Same thing which is happened here, right? It makes into parallel line. Then the prism, some diffraction in the refraction happens. After the refraction, now the light path changes because of the refraction. Light path changes. Now there's a focusing mirror, and from the focusing mirror, same as here on the focal plane, the light will be focused. And exit slit will be keep here. Now the desired wavelength with desired lambda value can be exit from the exit slit, right? So same thing, only the orientation is different. And here, when we do the wavelength scan, what we can do, we can change the position of the exit slit, position or angle of the exit slit. By changing the position or angle of the exit slit, then we can choose different wavelengths. So when we choose different wavelengths which passes from the exit slit, now we can do the wavelength scan in a wavelength range, particular wavelength range, using this monochromator, right? Okay, I hope it's clear what is happening here. And it's really important to understand what is happening. And I hope it's clear. Yeah, we talk about the components and the reflection grating. Reflection gratings, light hits grating and light is dispersed, and tilt grating to vary which lambda is passes at exit slit during the scan. So we can tilt that one also, the grating, by tilting the grating also. Yeah, instead of changing the exit slit, we can keep the exit slit in a constant position, but we can change the grating. We can change the grating. When we change the grating, the angles will be different. When the angles are different, then the when the angles are different, when the then the wavelength which passes from the exit slit will be different. So we can do that one also. To do the wavelength scan, we can change the grating position also. Right. And the grating monochromators. And here are some examples of the grating monochromators that can be used. I just give you the names of the grating monochromator. And I told you, I will show you a zoomed in image of the reflection grating here. See, this is how the surface looks like. It has a rough surface, the grating surface, and the monochromatic beams. The incident light comes here, and it will diffract at different angles, and because of that diffraction, we will get the different wavelengths, right? And the grating monochromators examples are Shelley grating, concave grating, and holographic grating. Those are 3 examples of gratings that can be used in the monochromator, and the function is different. We will not go into detail of this, what is happening there, but what you can do, remember there are different types of grating monochromators, and those are the examples of grating monochromators. So that is enough for you. Okay. Yes. Right. Then, so we talk about the sources, wavelength selectors, and yeah, in the wavelength selectors, slits are there. Before talking the next, we have to talk about the sample cells. And before that, let's talk little about the slits also. And in the wavelength selector, we talk there's an entrance slit and exit slit. So these slits control the entrance of light into and out from the monochromator. So entrance slit control the entrance of light, and exit slit control the exit of light. So by controlling the slit, especially the slit width, we can control the quality of the spectrum. So slit width plays a really important role when we talk about the quality of the spectrum, right? And the entrance slit controls the intensity of light entering the monochromator and help control the range of wavelength that strike the grating. So entrance slit control the intensity and the range of wavelength which enters the grating. It says entrance slit is less important than exit slit. The reason is, it is okay, whatever the wavelength range comes to the grating can select the particular wavelength range which is interested. Therefore, entrance slit also important. But compared to the exit slit, it is less important, right? And exit slit plays a more vital role and more important role because it helps to select the range of wavelength that exit from the monochromator. So that one is more important than the entrance slit because that is the wavelength which goes to the sample, and based on that wavelength we will be able to gather information from the sample. Therefore, exit slit is more important than the entrance slit. And this slit can be fixed. Slits can be just fixed slits, and or it can adjust in width. The width of the slit can be adjusted. So by adjusting the width of the slits, we can change the bandwidth of the radiation and also the intensity. Right? When we increase the slit width, we will increase the effective bandwidth. So the best way is to decrease the slit width. By decreasing the slit width, we can decrease the bandwidth of the radiation that we are interested in. And also the height can be adjusted. So by changing the height of the slit, the light intensity can be changed. So those are the slit. What are the important things of the slits of the monochromator? And next thing we have to discuss is the source. And since it's already 12:15, what we can do, let's discuss the source next day. And so let's see. So we discussed this, not the source. Next, we already discussed the source. We have to discuss the sample cell, right? I'm sorry. Sources we discussed. Wavelength selectors we discussed. What we have to discuss is sample cells, detectors, and the signal processor. And these three, let's discuss next day, right? So any questions from today's thing? No? Okay, and I will upload this one, this material also. I'll try to upload it today, and maybe I will be upload this one today. So go through the previous lecture notes and this one. And if you came across with any question, you can email me. And please check whether all of you have the access to the Google Classroom. And in the Google Classroom, so far I posted 2 lectures, and see whether you can see it and whether you can download it. If you have any difficulty in downloading it, and if it is not visible to you, please let me know, and I'll try what I can do next if it is not possible. And also, if you have any question, you can email me, and I will give you a tutorial for this one. My plan is to discuss the tutorial on the 5th day. Today is the 3rd day. Yes, we have 2 more days. My plan is to discuss the tutorial on the last day. But if in case, if I couldn't finish all the theory parts on time, is it okay for you to have another different date? Because this time we will not be able to get, because you have to start the next lecture. What do you think? Can we arrange different date for the tutorial? Is it okay for you? It doesn't matter, even after 4 is also okay with me.
It's okay, madam.
Yeah, let's see how the time goes, and I'll try my best to do the discuss tutorial. Still I have not prepared the tutorial. I will prepare it and I'll discuss the tutorial. And also there's another option. I will give you the tutorial, because this one is for the next semester. We can discuss the tutorial when you guys come physically to the campus. Which one you prefer? Discuss the tutorial online, or when you come physically to the campus? Which way is good for you? Then we can have some review session also along with the tutorial. What do you think? Which one is better? Do it online, or after you come back?
Madam, I think it's better if we do that after we come to the university, because so we can refresh our memory also.
Yeah, yes, because still you have to finish your first semester exams also, right? You did only one exam.
Yes, madam.
Yes, you did. So you have to finish that one. And also, yeah, I think because when I prepare, I have not prepared the tutorial yet. When I prepare the tutorial, I will try to cover everything that I teach in the lecture. Then by answering the tutorial, when we have the tutor section after you come back, then you will be able to refresh what you have learned. Yeah, I also think it would be better. So if you agree with that, then let's go that way. Okay. Right. Yeah.
Madam, one more clarification, madam.
Yeah.
In the Google Classroom, madam, we cannot see the lecture notes, but we have received, I received it as an email. The lecture notes I received as an email, but when I go to the Google Classroom, I cannot see the lecture notes, madam.
Okay, I shared it in Google Drive.
Yeah, I received the Drive link as an email, but
okay.
We are not seeing it in the Google Classroom, madam.
Yes, okay, I also see, that's why I asked you, in the previous lecture also for the chemometric one, I upload in different way. Now I see I have done something different. Let me check it again, and I'll try to change the way I am posting, right?
Okay.
Because that's why I asked you, because I noticed I uploaded this morning and I feel that I am following different things, I'm doing different thing, and I also couldn't see. Normally the lecture materials can be seen in the classroom when we have the Google, when you open the Google Classroom, but it was in the Google Drive. Yeah, I'll try to change that one, change the way I am uploading. Right, and please check whether you, but in the Google Drive also still you can download it, right?
Yes, madam. Yes, we can download.
Okay. Okay. All right. Okay, then, and if you don't have any question, we can wind up the session. Right? Yeah. Then have a good day.
Thank you, madam. You too.
You're welcome.
Thank you, madam.
You're welcome. I'll end the meeting.